It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good evening, everybody. Welcome to Tibbetts Physics. What is crappin'? Today, we're going to talk about the law of reflection. Have you ever noticed when you bounced a ball to somebody else that the angle you bounced it at is the same angle they catch it at? And that's based on the law of reflection. So we could define it as the angle of incidence we'll call that theta sub I. We'll draw a picture of what that means in a second. That's the incoming angle, is equal to the angle of reflection. We'll label that theta sub r. That's the angle it bounces off at. But the key thing is that these two angles are relative to the normal. And if we remember, the normal is a line that's perpendicular to the surface. So if we want to write an equation, we can simply say theta I is equal to theta r. Let's draw a picture to label everything, and then do a few examples together. So if this black line represents our mirror, we'll draw our incoming angle, or incoming light ray. And then where it hits the mirror, we're going to draw a perpendicular line relative to the surface of the mirror. That's called our normal. The angle of incidence is the angle between the light ray and the normal, so that's theta sub I. And then the reflected ray, theta sub r, is also between the normal and the reflected ray. So theta sub I equals theta sub r. So let's do a couple of examples. Let's say for the first one we're given that the angle of incidence is equal to 35 degrees. And we want to find theta sub r, but let's also find theta sub I plus theta sub r. And then let's also find the angle relative to the horizontal line, or relative to the surface. So let's draw our mirror, our normal, and theta sub I is 35 degrees. Oops. And we know theta sub r will equal theta sub I. So our reflected ray will equal our incoming or incident ray. So first part we can say is theta I equals theta r, which equals 35 degrees. If we want to add them up, that's the second part, theta I plus theta r. That's 35 degrees plus 35 degrees. That equals 70 degrees. And the last one, we want to find the angle relative to the surface. I'll just label it theta sub s. And that's between the horizontal, or the surface, and the light ray. So theta sub s. We know the total angle between the surface and the normal is 90 degrees. So theta surface is just 90 degrees minus theta sub I. So 90 degrees minus 35 degrees gives us 55 degrees. Okay, let's do another example, except this time we're given the angle relative to the surface instead of the angle of incidence. So theta surface, let's say, is 40 degrees. And we want to find theta I, theta r, and theta I plus theta r. The reason why we're doing all these examples is because even though the equation is easy, theta I equals theta r, we just want to make sure we're looking at the right angles based on the question we're given. So let's draw our angle, our incident light ray, and that's theta I relative to the normal. And our reflected light ray, that's theta r relative to the normal. In this problem, we're given theta surface, the angle between the surface and the incoming light ray. So theta s is 40 degrees. And again, we know the angle between the surface and the normal is 90 degrees. So theta I will be 90 degrees minus theta surface. So 90 degrees minus 40 degrees gives us 50 degrees. And we'll call that part A. And then if we want to find theta I or theta r, we now know theta I equals theta r. So that's going to be 50 degrees. And the last step, if we want to add them up, oops, just 50 degrees plus 50 degrees. So theta I plus theta r, 50 degrees plus 50 degrees gives us 100 degrees. So that's the law of reflection in a nutshell. But why don't we look at what really happens in terms of why is it that theta I equals theta r. So what we're going to do for this is set up a thought experiment by Richard Feynman and his theory on quantum electrodynamics, or QED. And in here he discusses how theta I equals theta r really works, using quantum electrodynamics. So what we're going to do is draw a long flat mirror, and we're going to have a source of light on the left side of the mirror. We'll label that S for source. And then on the right side we're going to have a detector that's like your eyeball, you detecting the lights. And what we could do is we're going to put a mask in between the source and the detector. So this way we can't shine light straight from the source to the detector. It has to bounce off the mirror. Now we just saw that theta I equals theta r. So that's going to happen right in the middle of the mirror, where we get theta I equals theta r. But light doesn't necessarily have to behave that way. The light can also go beyond the mirror towards the left and then bounce back up towards the detector. And notice if we were to draw a normal that theta I doesn't equal theta r. We could also do the opposite. Light could go beyond the detector and then bounce back up towards the detector. And again, notice theta I doesn't equal theta r. So if we were to draw every single option of what the light would look like as it hits the mirror and then bounces off the mirror towards the detector, we could make a graph of position on our x-axis, and then our y-axis will be time. And as we could see, the light that bounces off in the middle of the mirror, where theta I equals theta r, will require the least amount of time. The light that bounces off towards the left side of the mirror would take the longest, and the light that bounces off on the right side of the mirror would also take the longest. So if we were to plot a graph of this, we would just get a curve where we could see that it takes the least amount of time when theta I equals theta r, and then the most amount of time as we get farther and farther from that angle. So what happens is that all these probabilities cancel each other out with all the probabilities on the right side, leaving us with theta I equals theta r is the most likely outcome. So that means potentially that these other outcomes, they do exist, but they're just a lot more rare to happen compared to theta I equals theta r. So now let's look at how images are formed in different types of mirrors. The first mirror we'll look at is just a flat mirror, just like a bathroom mirror. So images formed by mirrors. And the first one again will be a flat mirror. What we're going to do is draw a vertical flat mirror, just like a bathroom mirror. We're going to use the letter P to represent the object in front of the mirror. So this would be like you standing in front of the mirror. Now the light that is reflected off of you and then hits the mirror is what forms the image. So we're going to draw horizontal parallel lines for now. That just represents light that's being reflected off of you and then hits the mirror. Let's draw 3 of them. Now light is reflecting off you in all directions. We're just going to look at the important ones. So let's also look at light that's reflected off of you at an angle and then hits the mirror. We're going to keep the angle the same as best we can. Now these ones, because they're reflected off at an angle, or because they're incoming at an angle, they're going to reflect back relative to the normal. So if you drew the normal for each one, that's the green line, we can see they're all going to reflect off the mirror. And notice still, these green lines don't converge. When the light rays converge is when we see an image. So what we have to do is go behind the mirror and see what the light rays do behind it. The purple light rays, the parallel ones, if we were to trace the reflected ray behind the mirror, it would just be a horizontal line. So we'll do our 3 purple light rays. And then we want to draw back the green reflected rays behind the mirror. And put a point where they intersect with the pink rays. Sorry. And if we were to do this a whole bunch of times, we would then get an image formed. And the image we see is going to be the reverse of our object. So that's why when you look in a mirror, you see yourself facing yourself. So in order to understand how this works, imagine that you projected yourself behind the mirror, kind of like Inside Out Boy, to see what your image actually looks like. Because we see you behind the mirror, this is called a virtual image. So it's not a real image. Okay, so why don't we look at 2 other mirrors? They're both going to be curved mirrors. The first mirror we'll look at is a concave mirror. In this case, the mirror bends or caves inwards. That's a bit dramatic. So we'll draw our incoming light rays. And what happens for a concave mirror, just like any mirror, they bounce backwards. They're going to bounce back. Oops, let me fix that one. Relative to the normal. And the purple middle one will just bounce straight backwards because it's hitting right on the normal. And what happens is where all the light rays converge, or the reflected rays converge, that gives us our image. In this case, because they converge in front of the mirror, reflected light rays, converge in front of the mirror, that gives us a real image. What that means is that if you were able to put a piece of paper right here, or a note card or something, you would get an image formed in front of the mirror. And that's how those optical illusions work. If you have two cone-shaped mirrors, one on the bottom, one on the top, with a hole on the top, and you see if you have an object somewhere inside this contraption, you'll see the object floating on top of the mirror. So what you're seeing is an actual real image, not really an optical illusion. Okay, the next mirror we'll draw is the opposite. That's a convex mirror. This mirror bows outwards. So we're going to draw 3 light rays hitting this mirror. And in this case, what happens when they reflect backwards is they diverge away from each other. So they're not going to converge in front of the mirror. But just like the flat mirror, we could continue the reflected rays behind the mirror. And what happens is they're going to intersect at a point. That's called a focal point. Notice it's behind the mirror. So we can say rays intersect behind mirror, forming a virtual image. Sorry, virtual image. And what that means is that they reflect behind the mirror, so it's not a real image. There's no image formed outside of the mirror. And that's it for this video. Hope you found it useful. If you did, please like and subscribe, and I'll see you next time. See ya.